Putting everything together gives us the molecular orbital diagram for hydrogen, or H2, which is shown in the figure below. Just like an atomic orbital diagram, the molecular orbital diagram shows us the relative energy and the number of electrons in each molecular orbital. So taking a look at our MO diagram, we see that the atoms, which are used to form the molecule H2, are located on the outsides of the MO diagram, as we see here. Since H2 is formed from two hydrogen atoms, we have two 1s atomic orbitals. And these can then combine constructively to form a bonding molecular orbital, and, as we see here, or destructively to form an antibonding molecular orbital, as we see here. Since the bonding MOs stabilize the system, they are lower in energy than the atomic orbitals from which they are formed. And since the antibonding MO destabilizes the system, they are higher in energy than the atomic orbitals from which they are formed. We can see here that the MO diagram also shows the atomic orbitals from which each molecular orbital is formed, and those are shown from the tie lines, which are represented by the dotted lines. So the 1 sigma G bonding MO is formed from the 1s atomic orbital from one atom and the 1s atomic orbital from the other atom, and the 1 sigma U star antibonding MO is formed from the 1s atomic orbital from one atom and the 1s atomic orbital from the other atom. In order to place our electrons in our molecular orbitals, we use exactly the same rules that we do to fill electrons in our atomic orbitals. Namely, we follow the Aufbau principle, which states that we filled our molecular orbitals in order of increasing energy. In other words, we go from lowest energy to highest energy. Next, we follow Hund's rule of maximum multiplicity, which states that when we have orbitals of equal energy, we first place one electron in each orbital with spins parallel, or all spin up. Then, only when our molecular orbitals are half filled, we begin to pair the electrons. Finally, we follow the Pauli exclusion principle, which states that each orbital can only hold a maximum of 2 electrons. And when we have 2 electrons in each orbital, they have to have opposite spin. So the first electron in an orbital will be spin up, and the second electron in an orbital will be spin down. Now, once we have our molecular orbital diagram, we are also able to write a molecular electron configuration. A molecular electron configuration shows the type of molecular orbital and the number of electrons in each orbital. So, for example, hydrogen, or H2, would have the molecular electron configuration of 1 sigma G 2, meaning that there are 2 electrons in the 1 sigma G bonding molecular orbital. For electrons in antibonding MOs, we typically drop the asterisks for the antibonding molecular orbitals. And so these are typically not included in the molecular electron configurations. Molecular orbital diagrams also allow us to calculate the bond order of the molecule. The bond order is defined as the measure of stabilization that results from the formation of the molecule. The equation for calculating the bond order is the bond order equals 1/2 times the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. The term 1/2 is required because it takes 2 electrons to make a covalent bond. Once we've calculated the bond order, if the bond order is greater than 0, the molecule is stable. If the bond order equals 0, the molecule is not stable. In other words, it cannot exist. A couple important points to remember for bond order. The higher the bond order, the more stable the molecule. The stronger the bond, the greater the bond energy, and the shorter the bond. Next, we want to fill in the MO diagram for hydrogen. Just as a reminder, the atomic orbitals are on the outside, as we see here, and the molecular orbitals are in the middle, and that's really the part that we're interested in. And the 1 sigma G represents the bonding MO, and the 1 sigma U star represents the antibonding MO, as we see here. Now, hydrogen, or H2, is composed of 2 hydrogen atoms. The electron configuration for hydrogen is 1s1, showing us that each hydrogen contributes 1 valence electron. And that electron for the hydrogen atom, before it's formed a molecule, goes in the 1s atomic orbital, as we see from the electron configuration. The other hydrogen atom also has an electron configuration of 1s1, and we see that that electron is also filled in the 1s atomic orbital of the other hydrogen atom. This tells us that there are 2 valence electrons in H2. And those 2 electrons we now fill in the MO part of the diagram. So according to the Aufbau principle, the first electron goes in the lowest energy molecular orbital, which happens to be the 1 sigma G bonding MO. And that's where that electron would go. Now, the second electron would also go in this molecular orbital, but this one has to go spin down, or spin minus a half, according to the Pauli exclusion principle. And so now this is the completed MO diagram for H2. We can also write the electron configuration for H2, which is 1 sigma G2, suggesting that there are 2 electrons in the 1 sigma G bonding molecular orbital. And this is indeed what we see in the MO diagram, 2 electrons in the 1 sigma G bonding MO. And that's what the bonding MO looks like. Finally, we can also calculate the bond order of H2. And as you recall, the formula for bond order is 1/2 times the number of electrons in bonding MOs minus the number of electrons in antibonding MOs. In this case, that would give us 1/2 times 2 electrons in the bonding MO minus 0 electrons in the antibonding MO, giving us a bond order of 1. In this example, we are asked to use MO diagrams to find the bond orders and predict the stability of He2+ and He2. Furthermore, if they do exist, then we are asked to write down the electron configuration for the molecule. The strategy we're going to use is number 1, to find the number of valence electrons in each species, and then to distribute them to the molecular orbitals following the rules for filling orbitals, namely the Aufbau principle, Hund's rule of maximum multiplicity, and the Pauli exclusion principle. Next, we're asked to calculate the bond order and then predict the stability of the molecule. And then finally, we will write the electron configuration using the format shown here, where sigma G and sigma U represent the bonding and antibonding molecular orbitals, respectively. And the superscript X represents a number of electrons in each of the orbitals. So we can imagine that He2+ is formed from 2 atoms. The first atom would have the electron configuration 1s2, showing 2 valence electrons in the 1s atomic orbital, which we would place in one of the 1s atomic orbitals. The first electron would be spin up, and the second electron, according to the Pauli exclusion principle, would be spin down. The next atom, we could imagine, would be present as He+, which would have an electron configuration 1s1, which we would place in the other 1s atomic orbital. So we have 1 electron in the 1s atomic orbital. This tells us that there are a total of 2 plus 1 equals 3 valence electrons in our He2+ molecule. And we can see that they're located 1, 2, 3. So those are where the electrons start, because those are located on the atoms. However, to create our MO diagram, we want to place those 3 electrons in our molecular orbitals. And we would start by placing the first electron in the lowest energy molecular orbital, which happens to be the 1 sigma G bonding molecular orbital. So the first electron would be placed spin up, or spin plus a half. And then, according to the Pauli exclusion principle, the second electron would also be placed in the 1 sigma G bonding molecular orbital, but that would be placed spin down. The third electron would be therefore placed in the next lowest energy molecular orbital, which would be the 1 sigma U star antibonding molecular orbital, and that would be placed spin up, or spin plus a half. So this completes the MO diagram for He2+. We can write the electron configuration for this system, which is He2+ has the electron configuration of 1 sigma G2, 1 sigma U star 1. This tells us that there are 2 electrons in the 1 sigma G bonding molecular orbital, and here we see the 2 electrons in the 1 sigma G bonding molecular orbital, and 1 electron in the 1 sigma U antibonding molecular orbital. And here we see the 1 electron in the 1 sigma U antibonding MO. You'll notice that in the electron configuration we've dropped the star notation, or the asterisk, and this is because the asterisk really isn't a part of the notation for the MOs. In the case here, we are using it just to remind us that it's an antibonding MO. Finally, we can calculate the bond order for the system. And as you recall, the bond order is equal to 1/2 the number of electrons in bonding MOs minus the number of electrons in antibonding MOs. So using that formula, we see that we have 1/2 times 2 minus 2, because there are 2 electrons in the 1 sigma G bonding MO and we're going to subtract the 1 electron from the 1 sigma U star antibonding MO. And this gives us a bond order of 1/2. Next, we'll take a look at the MO diagram for helium, which is shown here. So we can imagine that our He2 molecule might be composed of 2 helium atoms. The first helium atom has the electron configuration 1s2, telling us that there are 2 electrons in the 1s atomic orbital, shown 1, 2. And the second atom would also have the electron configuration 1s2, and so the 2 atom electrons for that atom would be shown in the other 1s atomic orbital, showing us that there are 2 plus 2 equals 4 valence electrons that we have to distribute in our molecule. So in the atoms, they both start in the 1s atomic orbital on one atom and the 1s atomic orbital on the other atom, and now we have to place them in the molecular orbitals, which are the ones in the middle. So starting with the lowest energy molecular orbital, we're going to place the first electron in the 1 sigma G bonding MO, which will be placed in that MO spin up, or spin plus 1/2. Second electron will be placed spin down, also in the 1 sigma G bonding MO. The third electron would go in the next lowest energy molecular orbital, which is the 1 sigma U star antibonding MO, and so that would be placed spin up. And finally, the fourth electron will be placed spin down, again in the 1 sigma U star antibonding MO. And this is the completed MO diagram for He2, or helium. We can see from the MO diagram that He2 would have a bond order of 1/2 times 2 minus 2, because there are 2 electrons in the 1 sigma G bonding MO and 2 electrons in the 1 sigma U star antibonding MO. This gives us a bond order of 0, telling us that this molecule is not stable and therefore cannot exist. Just like atoms, molecules can also be classified as either paramagnetic or diamagnetic. Just as in the case of atoms, paramagnetic molecules are determined based on their electron configuration. If a molecule has 1 or more unpaired electrons, it is classified as paramagnetic, and if all the electrons in a molecule are paired, then it is diamagnetic. Experimentally, paramagnetic materials can be distinguished by their attraction to a magnetic field. So we see here that liquid oxygen, so that's O2 that has been supercooled into a liquid, will be attracted to the magnet as shown in this figure. And diamagnetic materials, by contrast, will be repelled by a magnetic field. And water, which is an example of a diamagnetic material and is present in most living organisms, we see here that we have a frog which is suspended on top of a superconducting magnet. So it's a very powerful magnet, and we see that the frog, which is mostly composed of water, is repelled by being suspended in the air, like magic. In this slide, we look at the energy between bond order, bond length, and bond energy. So looking at a series of homologous carbon-oxygen bonds, we see that moving from the bond order of 1, 2, and 3, the average bond length decreases from 143 picometers to 113 picometers. And since the bond energy is inversely proportional to bond length, we see that the bond energy increases from 358 kilojoules per mole to 1,070 kilojoules per mole as we move from a bond order of 1 to a bond order of 3. The same trend can be observed for other carbon bonds. So here we're looking at carbon-carbon bonds with bond orders of 1, 2, and 3 respectively, and we see that the bond length decreases while the bond energy increases. And looking at the nitrogen bonds, we see again going from a bond order of 1 to a bond order of 3, the bond length decreases and the bond energy again increases. So this is just a reminder that the bond order is inversely proportional to the length of the bond and is directly proportional to the strength of a bond. So a bond order of 1 will have a relatively long bond and will have a small bond energy, whereas a bond order of 3 represents a short bond with a high bond energy. Okay? So the higher the bond order, the more stable the molecule, the stronger the bond, the greater the bond energy, and the shorter the bond. Moving to MO diagrams for period 2 elements, we see that the first element in period 2 is lithium. And so we can imagine that we might be able to form an Li2 molecule, at least in the gas phase. So lithium has 3 electrons, as it has the electron configuration 1s2, 2s1. And the 3 electrons in the atomic orbitals for lithium are shown here, 1s2, 2s1. Okay. The other atom would be identical, so it would have the same electron configuration. Okay. And this would tell us we have 6 electrons, 3 from each atom. And so the MO diagram for Li2 is shown here. Now, you notice that the 2s orbitals are very similar to the 1s atomic orbitals, except that they are larger. And so we might expect that they form bonding and antibonding MOs very similarly to those formed from the 1s atomic orbitals. The main difference is that these would be higher in energy because the 2s atomic orbitals are higher in energy than the 1s atomic orbitals. Okay. And in this case, the bonding MOs formed from the 2s atomic orbitals are labeled 2 sigma G. 2 because this represents the second lowest bonding sigma molecular orbital. And the antibonding MO is labeled 2 sigma U star because it is the second lowest energy antibonding sigma atomic molecular orbital. Okay. Now, even though we've shown the molecular orbitals formed by the 1s atomic orbitals, they actually don't contribute very much to bonding. And this is because they actually represent core electrons, right? So in the case of lithium, the 1s atomic orbitals are core electrons. And as a consequence, the overlap between the 1s orbitals is very poor. And so they really don't contribute anything to bonding in the molecule. As a consequence, we usually just show the upper half of the MO diagram, which represents the valence electrons. So we see here that each lithium atom has 1 valence electron, and so our molecule would have 2 valence electrons, which we would place in the 2 sigma G bonding molecular orbital, as shown here. In this case, the bond order for this system is 1/2 times 2 electrons in the bonding molecular orbital minus 0 electrons in the antibonding molecular orbital, which gives us a bond order of 1. So let's look at the MO diagrams for Li2 and Be2, just to see how we would make these for second period elements. So Li2 is composed of 2 lithium atoms. The first lithium atom we could imagine as having an electron configuration of 1s2, 2s1, and here we can see that the 1s electrons are core electrons, and the electron in the 2s atomic orbital is the valence electron. So that gives us 1 valence electron in the 2s atomic orbital, which we represent here. The other atom also has the electron configuration 1s2, 2s1, so it also has 1 valence electron in the 2s atomic orbital, which we put here in the 2s atomic orbital. This tells us that Li2 has 2 valence electrons. 1 plus 1 equals 2 valence electrons, and those valence electrons on the atoms are located on these parts of the MO diagram. So now what we want to do is place those 2 valence electrons in our molecular orbitals to complete our MO diagram. Starting with the lowest energy molecular orbital, which is the 2 sigma G bonding molecular orbital, we place our first electron, which is placed spin up, and then the second electron is placed spin down in the same 2 sigma G bonding MO. And that completes the MO diagram for Li2. The electron configuration for Li2 for the valence electrons is therefore 2 sigma G 2, indicating that there are 2 electrons in the 2 sigma G bonding molecular orbital. And as we see in the MO diagram, we have 2 electrons in the 2 sigma G bonding MO. The bond order we can also calculate as 1/2 times 2, which represent the 2 electrons in the 2 sigma G bonding MO, minus 0, as there are 0 electrons in the 2 sigma U star antibonding MO. So this gives us a bond order of 1 for Li2. Using the same approach, we can complete the MO diagram for Be2. Each beryllium atom has an electron configuration of 1s2, 2s2, and we can see that the electrons in the 1s atomic orbital are the core electrons, and the electrons in the 2s atomic orbital are the valence electrons. and indeed beryllium is in group 2, indicating it should have 2 valence electrons. So those 2 valence electrons would be placed in the 2s atomic orbital. There's the first electron, and the second electron would be placed in the same orbital, but spin down, or spin minus a half. The second beryllium atom also has the electron configuration 1s2, 2s2, and so again we would put 2 electrons in the 2s atomic orbital on the right. This tells us that Be2 has 4 valence electrons to distribute. 2 plus 2 equals 4, and we see 2 electrons in the 2s orbital, another 2 electrons in the other 2s atomic orbital, giving us 4 electrons to distribute in our molecular orbitals. So starting with the lowest energy molecular orbital, which is the 2 sigma G bonding MO in this case, we see that the first electron goes in the 2 sigma G bonding MO. The second electron is placed spin down in the 2 sigma G bonding MO. The third electron is placed in the next lowest energy molecular orbital, which happens to be the 2 sigma U star anti-bonding molecular orbital. And the fourth electron is also placed in the 2 sigma U star anti-bonding MO, but it would have to be placed spin down. So this completes the MO diagram for Be2. We can see that in this case the bond order equals 0, as we have 1/2 minus 2 electrons in the bonding MO minus 2 electrons in the anti-bonding MO gives us a bond order of 0. And in this case, the molecule is therefore not stable and it cannot exist.